we're starting in topic 24 today. In this lesson, we're going to be looking at computing the volume and surface area of prisms. Up until this point in geometry, we've been studying what is called plane geometry. Now, not like plane as in simple, that would be spelled P-L-A-I-N, but plane as in P-L-A-N-E is a geometrical figure, and we know it's a figure that extends forever in both directions. It's a flat surface that has an infinite length and an infinite width to it. So far in geometry, we have been studying things like points and segments and lines and rays and polygons and circles. So those are all things that are in plane geometry. But as you can see in your world around you, we have many objects that extend beyond just a single plane, that are not just flat surfaces. So we have to explore those in 3 dimensions, or in what we call space. 2 important groups of 3-dimensional figures in geometry are called prisms and cylinders. And so our first animation here will show us their characteristics and some terminology associated with them. You'll be answering questions 1 and 2 in your notes here. So if we start with a polygon in a plane and we translate it, remember that's just a slide, up in that plane, then we create a plane parallel to the one we started with. If we connect those planes together at the vertices, then we create what is called a prism. So we started off with a pentagon, we translated that pentagon, we connected the new pentagon with the old one, and we created a prism. Now, the original polygon and the one that was translated are called the bases. And we can see here those bases are parallel to one another. And again, those bases are pentagons. And so the prism is named after whatever shape the base is. So since our base is a pentagon, this is called a pentagonal prism. If the base was a hexagon, it would be a hexagonal prism. If the base was a triangle, it'd be a triangular prism. So you always name the prism based on what the base is. Now, the base is not always the top and the bottom. I could just take this prism and tilt it over on its side, and the bases are still the pentagons. So it's whatever the parallel faces are called the bases. Okay, so the ones going along the edges, which are all rectangles, are called lateral faces. So we have a total of 7 faces in this prism, but 2 of them are called bases, and the other 5, those rectangles along the edges, are called lateral faces. We have 5 of them because that's how many sides our base had. So if it was a hexagonal prism, we would have 6 faces along the sides. If we had a triangular prism, we'd have 3 lateral faces. So you're going to have the number of lateral faces based on whatever your base has as its edge length, or edge number, I should say, not length. Now, when we have 2 faces come together, if it's 2 lateral faces coming together, they form what are called lateral edges. So these segments where those lateral faces come together are called lateral edges. So we have 5 of those along the sides of this figure. We also have what are called base edges, and that's where our base meets a lateral face. Those are, again, segments. We have 5 along the top and 5 along the bottom, so we have a total of 10 base edges. So altogether, we have 15 edges, 10 that are base edges and 5 that are lateral edges. Now, this figure is what is called a right prism. And the reason why it's called a right prism is because our lateral edges are perpendicular to the base edges where they meet. So we form right angles right here. This is mainly what we're going to be studying in this topic is right objects or right 3D figures. We are not going to be studying very much what are called oblique prisms. So this is an oblique prism. Now you can see where this lateral edge meets this base edge. We form an obtuse angle here. Sorry, the bell's ringing. And we have an acute angle here. So these are no longer right angles, so this is called an oblique prism. It's literally like you took that prism and kind of squashed it off to the side. So it's still called a pentagonal prism. It's just oblique now instead of right. Our bases are still parallel to one another, however. So let's see what we should have on our notes so far. So using this prism, it says how many bases are there, and there are 2, and remember they're both pentagons. So when you name that base, you're going to be naming the points, the vertices names in order, either clockwise or counterclockwise, and usually you just do it alphabetical order. So we could name this A, B, C, D, E. That's one of our bases. The other one would be J, F, G, I, H, I. How many lateral faces are there? Remember, those are along the sides here. Again, if we tilted it along the side here, it would still be those rectangular faces. Your bases are always parallel to each other. So we have 5 lateral faces. They are all rectangles. And so when we name that rectangle, again, we are going to name the 4 endpoints. So we could name this one DCHI, for example, there on the front. DCHI. How many lateral edges are those? Remember, these are these segments where 2 lateral faces join together. So segment DI is 1 lateral edge. And remember to use the segment bar, because if you leave it off, you're talking about a measurement, not an edge then. And so there are 5 of those rectangular lateral edges along the sides there. How many base edges? Base edges are where the base meets the lateral face. So these are these segments, like right here. 1 base edge would be that segment I just highlighted, segment ED. There are 5 along the top, 5 along the bottom, so there are 10 base edges. So all together, we have 15 edges in this prism. All right, so let's look at our next animation is going to answer question 3 in your notes. I guess we should go ahead and answer number 2. Sorry, I forgot to do that. What's the difference between a right prism and an oblique prism? A right prism is when a lateral edge is perpendicular, and remember upside down T is a symbol for that, to the base edge. You form right angles where they meet. So where segment DI and CD intersect, they would be right angles when that's a right prism. An oblique prism would obviously not have that relationship. All right, so in this animation, we're going to construct a cylinder, and it's constructed very similarly to what we just did with the prism. We're going to start with a circle in the plane, and we're going to translate that circle. And so when we connect the bases there, which are circles this time, then we create a cylinder. So this is a cylinder. The cylinder, of course, has 2 bases just like a prism does. This time the bases are not polygons though, because remember polygons are made up of segments and circles don't have segment sides. So the bases are circles in a cylinder, and they're parallel to each other again. The lateral surface this time goes along connects the 2 circles, I should say, and we'll talk about what that surface looks like when we fold it out. Now, a right cylinder is when you connect the 2 centers of your parallel circle bases, and it is perpendicular to the radius here. So we call that the axis, and that just connects your 2 centers, and we have a perpendicular relationship there to that base. So that makes that a right cylinder. When it's not perpendicular to your radius on your base, then we have what is called an oblique cylinder. So very much like the prism we just looked at. And again, we're going to be mainly focused on right cylinders in this topic. So let's look at question 3 in your notes. The bases are the 2 circles that are parallel to each other. This is the lateral face that connects those 2. And then the axis would go from center to center. And when it's perpendicular to the radius of the base, then we have what's called a right cylinder. Okay, so in this topic, we're going to discover, or maybe even rediscover if you've looked at this before, some strategies and formulas that will help us compute volume and surface area of both prisms and cylinders. And then later, we're going to be looking at pyramids, which is like this figure here. And so it says, how are cylinders similar to or different from other prisms? Well, we've talked about it already. We know that in a right cylinder, we have those bases that are, just a second, I'm sorry. Okay, sorry. So cylinders are similar to other prisms in the fact that they have two bases. Those bases are parallel to one another. And another similarity is the lateral faces. So in lateral faces of prisms, they're going to be rectangles. And remember, even if they're a square is a rectangle. So the lateral faces of prisms, right prisms, I should say, are always going to be rectangles. Well, with a right cylinder, when you take off that lateral face and lay it flat, it is also one giant rectangle. So think of like a soup can. If you take the label off of it and lay it flat, it would be a rectangle. So it says, what geometrical attributes of prisms and cylinders are we often interested in measuring? And the two most common are the volumes, which is the space inside, and the surface area, which is the amount of space in the faces of that object. So like if you were going to paint the outside of it, that would be surface area. If you're going to fill it with liquid, that would be volume. So let's look at question 4 in your notes. It says, designer works in new product development for the Uncommon Grounds Coffee Company. She is designing a new travel size package for sugar cubes, which are among the company's most popular products. We might need to talk to Ms. Wilkins about this. They just opened up a food truck with coffee. It says each sugar cube is a 1 centimeter by 1 centimeter by 1 centimeter cube of sugar. So in other words, each cube contains 1 cubic centimeter, or 1 centimeter cubed of sugar. So D plans to for the new travel size package to contain 48 of these sugar cubes, and she's looking at different ways to package them. So which of the following 3-dimensional shapes do you think would work best for the sugar cube packages? A triangular prism, a cylinder, an oblique rectangular prism, or a right rectangular prism? Well, a triangular prism is going to have triangular bases, right? And we have these little cubes that we wouldn't be able to pile them in there very well, right? Because we have 90-degree angles where those edges are meeting on the cubes, and we wouldn't have that with a triangular prism. A cylinder has curved edges, so that probably is not the best either. And remember, with an oblique rectangular prism, it's not going to be standing straight up. It's going to be squished off to the side. And so that'll affect how we can put those cubes in there as well. So I hope you agree with me that a right rectangular prism is probably her best bet. And we've talked about why that is. So you can answer that on question 4 in your notes. So she begins to experiment with different shapes for her packaging of these 48 cubes. And as she does so, she realizes the best shape is a rectangular box, like we just talked about. She begins building a different rectangular prism out of 48 sugar cubes. And each time she lays out a rectangular base layer of cubes and then adds more layers to that same size until she runs out of cubes. She finds that sometimes she uses all the cubes, and sometimes there's cubes that are left over. And so we're going to see whether we can figure out what happens and fill in the correct answers to these sentences in question 5 on your notes. So we have, let me get there. Here it says she finds out that when she starts with a what rectangular layer. So we can either do 3 by 4 or 3 by 5. But let's read on to see which one. It says she uses all 48 cubes when there are how many layers in all? Well, it's a 3 by 4. If we have 3 centimeters by 4 centimeters, that means we have 3 times 4, which is 12 centimeters squared in all. So that means we could put 12 cubes in that bottom layer. So 1 layer would be 12 cubes, 2 would be 24, 3 would be 36, 4 would be 48. We would use all of them, right, in how many layers did I just say? 4 layers, right? So we're going to use the 3 by 4 here. That's 12 cubes. 3 times 4 is 12. And 12